Hello, Mr. Kwan. This is Emiel Bril, and I'm going to teach you how to do calculus and vectors. The question that we are dealing with today is a rate of change question in terms of derivatives. The question goes as follows. The voltage across a resistor is V equals IR, where I is equal to 3.72 minus 0.02 T squared is the current through the resistor in amperes. R is equal to 13 plus 0.21 T is the resistance in ohms, and T is time in seconds. Now that we are given all the information we need in the question, we need to write an equation for V in terms of T, determine V prime of T and interpret its meaning for this situation, and finally determine each rate of change after 3 seconds, so for the voltage, current, and resistance. Let's start by highlighting all the key points, what we know and what we need to figure out. We're given all the variables and their equivalent equation as well as the context and units of measurement required. With this information, we will be able to answer this question properly. Now we have the equation for the current, the resistance, and the voltage. We also know that the current is measured in amperes and the resistance is measured in ohms. And if you're like myself, you'd have to urban dictionary that and realize that amperes is actually the long form of amp, and it's the flow of electrons in the unit, and ohms is the unit of resistance offered to current flow by a conductor. Our goal in part A of this question is to develop a function of the voltage in terms of time. Now we know that the voltage is equal to the current times the resistance, and the current is a quadratic function where the resistance is linear. Therefore, we know that the voltage is going to be a cubic function. Now, as you can see, we have simply executed the steps outlined very clearly in order to develop our equation of voltage. Part B of the question is asking us to determine the derivative of the voltage. But what is the derivative? Well, the derivative is the equation that models the instantaneous rate of change, or the slope, at every point of the function, so in this case our voltage function. In order to develop V prime of t, I used a combination of the sum rule and the power rule. V prime of t is a quadratic function, as it is 1 degree less than the voltage function. In context, the derivative, or V prime of t, represents the rate of change in voltage at different times, or as time changes. Part C is quite simple, as we are using what we already have to simply evaluate. The only information we are not provided with is the derivative of the current and the resistance. So let's start by solving them using methods from Part B. Of every derivative in terms of t, we simply need to evaluate at 3 seconds. We do this by simply substituting 3 for t. Pay close attention as we evaluate each function. This means that at 3 seconds, the voltage is decreasing at a rate of 0.8922 volts per second. At 3 seconds, the current is decreasing at a rate of 0.12 amps per second. Now, because the derivative of the resistance is a constant, at 3 seconds, the resistance remains the same at 0.21 amperes per second. Let's recap our strategy, our steps, and what we have done. We started off by determining the voltage function using the current and resistance function. Then we use various derivative rules, such as the sum and power rule, to solve V prime of t in its given context. And finally, we applied everything that we had done in parts 1 and 2 to evaluate at 3 seconds for both the current, resistance, and voltage. The concept of rate of change is universally applied. There are so many careers that use derivatives and rate of change along with things that you and I do every day. Rate of change can be applied to airplanes as well as flight paths. Rate of change is also used in the marine life industry. And of course, rate of change is used in business, stocks, and money. Virtually everything in every career you know uses rate of change. For example, looking back at airplanes, then changes in speed or altitude over a period of time is modeled through rate of change. Even IROC, the speed or the altitude at that particular moment. This is important because it can determine if the plane is moving too fast, too slow, or even how much gas the plane is using over the course of a period of time. Looking at marine life, you can graph the population change over 10 years and determine what the rate of change is. This is also important because it can provide important information to biologists, such as if the population is too high or too low, so they know what needs to be done. And most importantly, stocks, the percentage change at that particular moment or the lifespan of the company. Now this is very important because it can provide crucial information as to when you should buy or sell stocks. Rate of change is a very important tool and it's used in almost every single industry. Now Mr. Kwan, I understand that calculus can be very difficult at times, so if you have any other questions, don't hesitate to ask. Thanks, and I hope you enjoyed.